Hi. So this week for repeated measures ANOVA, we already know that ANOVA tests for differences between several means, but in this design, participants in the repeated measures participate in all conditions of an experiment, and they provide data at multiple time points, obviously, because they're in each condition. So in repeated measures ANOVA, the effects of the experiment are shown in the within participant variance rather than in the between group variance, because the within participant variance is made up of the effect of the manipulation from each condition and the individual differences in performance. So my research question for this week was, does the type of lighting one works in change productivity? And my four conditions were natural light within an office, so just the daytime light coming in, low artificial light in an office, so just like very dim, a dimly lit office, obviously from artificial lighting, and then high artificial light in an office from just like standard lighting. And then my fourth condition was being completely outside. So I have natural, low, high, and outdoor as my conditions above, and then my participants on the side. So I already imported the data, obviously, as I just showed you. And I'll talk about these packages when I library them down here, just so we don't have to wait for them to all load. I already cleared them. They're installed. So I loaded this package to run in ANOVA. The molt comp is for post hoc tests. The NLME is for in case you used a multi-level model later. PASTEX is for descriptive statistics. Reshape is for reshaping the data. And this is a problem. So the melt function is something that you need for the first step. And I have to detach and uninstall basically that in order to get Reshape 2 to work to reshape the data. Otherwise it won't run. So I had to add that in there too. So you don't need Reshape, you just need Reshape 2. And then the WRS is for the robust tests. So I attach my data set, and this is where we use the melt function. And for this analysis, we need the data to be in long format, and it's currently in wide format as the levels of the repeated measures are spread across the different columns as seen above. And the melt function allows us to specify the columns in the data that identify the characteristics of the scores, in this case from who they originate from, which is the participant, as I have labeled above here. So identify as participant, and then the columns that identify the actual scores, so the productivity scores that we see under each condition here. And my measured variables are the columns natural, low, high, and outdoor. So I have identified all of those 5 things below here, and I will run that, and that will create a new data set, and this shows all the participants. So now instead of having 10, there's 40 conditions because everyone is placed based on their variables, and you can see the different values. So there's all of them have been split up. So after this, we rename the columns in the new data frame, and I chose participant, light to indicate level of light, and then productivity, which is the score from each participant in each lighting condition. And then lastly, we convert the light variable into a factor, indicating the new data frame, light, and the levels of each lighting condition from the original data. So the long data converting to a factor, and then labeling the 4 different kinds of light. Next, we will look at the descriptive statistics for the separate groups. So we're going to look at productivity and light. That's what we're interested in comparing. So we can explore the effects of the type of lighting on productivity. Next, I set the create variables for each contrast. So we're setting the contrast in order to see the main effects that tell, or the effect that tell us where the differences in the groups lie. So for my data, I set contrasts that compared the true lighting, so lighting from the sun and in the natural and outdoor groups, combined compared to the artificial lighting group. So this is the fake slash real, and obviously the high-low lighting for the artificial lighting. So those two groups combined, and then the next contrast separates the high lighting from the low lighting, and the third contrast separates the natural lighting from the outdoor lighting. So then we have to set all three new variables into one variable in order to run these contrasts. So we bind these together to set a overall contrast for light. And we check to see if the contrasts are set correctly by putting the name of the variable created earlier, so the long RMA2, and looking at the contrast attribute that we were interested in, which was light in this case. So we're checking to make sure these are correct. And so from looking at the contrast, we know that positive numbers are compared with negative numbers, and a 0 means that the group isn't involved in the contrast. And from my output, we can see that the first contrast compares the natural and outdoor light to the low and high light. So 1, 1, negative 1, negative 1. And then the second contrast compares the low light to the high light. So low, high. And ignores the natural and outdoor lights with the zeros. And then the final contrast compares the natural light to the outdoor light and ignores the low and high light groups. So next we will create a model to run the ANOVA and receive the sphericity information. So using this function, we're going to get the ANOVA output and compute sphericity and the corrections for sphericity also. And so dv is the variable that contains the scores, so the outcome variable, and in this case the outcome variable was productivity, so that's represented by the variable productivity here. In the variable that identifies the participant to see where we're pulling the productivity and the light from is under this WID function. The within is light, and that's the variable or list of variables that represent the independent variables or predictors manipulated, so we know in the between groups. So we know that this is light. And then we want to set detailed to true because Andy said so, basically. Default is false, and it gives you a more detailed output if you set it this way, and then you set it to type 3 sums of squares. So after creating the new model, we run it to see if the output of the ANOVA and the sphericity information. So interpreting this, Mauchly's test for sphericity should be non-significant if we're going to assume that the condition of sphericity has been met, and we will look at the column with the significance value p. And we know that the value of 0.019 is less than the critical value of 0.05. So we then reject We're looking down here. So we then reject that the assumption of the variances of the differences between levels are equal, and the assumption of sphericity has been violated. So that's the W equals 0.17 and P is 0.019 in this case. So because of this, we can observe the corrections down below. Greenhouse and Geyser and Hohenfeld, the correction factor is applied to the degrees of freedom and used to assess the observed F ratio. So the closer the Greenhouse Geyser correction is to 1, the more homogeneous the variances of differences, and the closer the data is to being spherical. So because we have 4 conditions, the lower of the limit of the correction is calculated by 1 divided by 4, the number of conditions, minus 1, which is 0.33. So our calculated value from the output given below is 0.58, which is closer to the lower limit of 0.33 than the upper limit of 1, so therefore represents a deviation from sphericity. And this output also contains the Hohenfeld estimate, which is 0.71, as seen here, which is closer to 1 than the Greenhouse Geyser estimate. So we're also able to see the results of the ANOVA from the within subject variance, the sum of squares from the repeated measure effect of light tells us how much of the total variability is explained by experimental effect. And the value of 4,244.5, as you can see here, is the model sum of square. And there's also an error term next to it, which is the amount of unexplained variation across the conditions of the repeated measures variable. So the residual sum of squares is 735. The sum of squares are converted to a mean score by dividing degrees of freedom. The degrees of freedom for the effect of light is k minus 1, and k is the number of levels of the independent variable, so we've already decided this was 4, minus 1 is 3, and the error degrees of freedom is n minus 1 times k minus 1, so n is the number of participants, and k is obviously before, so 10 minus 1 times 4 minus 1 gives us the 27 that we see here for the degrees of freedom. And 3 was the first one we discussed. So the F ratio is obtained by dividing the mean squares of the experimental effect by the error mean squares, resulting in the F value of 51.97 right here. And this is compared against the critical value for 3 and 27 degrees of freedom. So the significance of F is 2.4 e to the negative 11, as we see here, which is significant because it is less than the criterion value of 0.05. So we can conclude that there was a significant difference between the 4 lightings in their ability to alter productivity, but this test does not tell us which lighting differed from each other, the other lightings. We also know that a violation of sphericity assumption makes the F test inaccurate. So for the data, the corrections in the observed F being significant of the P, 2.17 e to the negative 7 down here for the corrections. For the Greenhouse Geyser correction and the observed F being significant, P equals 1.34 e to the negative 0.08 for the Hohenfeld corrected p-value, and we would accept the hypothesis that the type of lighting affected the productivity of the workers, but the correction is liberal and sometimes accepts the values as significant when they are not significant. So Andy recommends taking an average of the 2 significant values to give a rough idea of which correction values give the most accurate answer, and since both of my values are so small, it should just be concluded that the F ratio is significant, because dividing these, it's still going to be a very, very small number. So next we will run the post hoc tests. And we use the pairwise t-test function. And we want to add true to reflect that the means are dependent here, identifying a paired t-test rather than an independent t-test, as we're used to. So from these results, we can see that the productivity level was significantly higher in the natural light compared to the low light at the p equals 0.006, as well as the highlight, p equals 0.0002, and the outdoor light, p is 6.6 e to the negative 0.8. The productivity in low light was not significantly different, however, than in highlight at the p equals 0.3, so it's greater than 0.05, but was significantly different than in outdoor light at p equals 0.003. Finally, the productivity in highlight was significantly different than in outdoor light, 0.003. So next, we are going to write a one-way ANOVA as a linear model. Here. So we're going to write that just as we normally would. But because this is a repeated measures ANOVA and we are trying to predict the productivity level from the type of the light worked in, we want to create a new model for the repeated measures ANOVA. So we have to account for the fact that the predictor, which is light, is made up of data from the same people and therefore dependent. And we are going to use the LME function to factor the dependency into the model. And we also want to indicate ML here as maximum likelihood estimation to use random and specify participant within the variable light, so the overall levels of the outcome of productivity vary based on those two. Including this tells the model that the data with the same value of participant within different levels of light are dependent, so we know that they're from the same person. And it's basically the same as the linear model as we've seen above, but we are indicating the term random with the participant and light to let the model know that the variable light is made up of the same participants and it's repeated across multiple times for the variable. So next we are going to create the baseline. Well, first create the baseline. So we want to see if light had an overall effect. So we need to compare the model that we just created to one in which the predictor is not included. So we're taking out light here and replacing it with 1. So that creates a baseline that we can compare these two against each other to see if light had an overall effect. So we're going to compare the two models to see whether adding the variable light as the predictor significantly improved the model by using the group means to predict the level of productivity. Does the model fit the data better than when we don't have the predictor? So is light important to have in the predictor? So this output shows us that the comparison of the baseline model and the other model that used light as a predictor and the AIC and the BIC tell us about the fit of the model, and since both values in the model that include light as a predictor are smaller, so these lower ones, than the ones included in the baseline, it tells that the fit of the model has gotten better when including light as a predictor. So the p-value is tiny, indicated here. And therefore light is a significant predictor of productivity, and we can conclude that the type of light worked in had a significant effect on the level of productivity based on the L ratio and the p-value. So we can further explore the model by running a summary of it. And the output shows the parameter estimates for the model. So most importantly from this, we can see the parameters for the 3 contrasts that we set earlier. So when we compare real lighting, natural, and outside combined, let me scroll. Right here. To artificial lighting, high and low combined, productivity was significantly different. The B value 1.80, T 27 degrees of freedom equals 2.18, P is 0.038. So across that line. From the descriptive statistics, which I referred to, it looks like that people were more productive in real light than artificial light. I did this all in a write-up. And the second contrast tells us that there's no significant difference in the productivity between low lighting and high lighting. So we can see that here, B equals 2.35, T 27 degrees of freedom is negative 2.01 here, and then the p-value of 0.054. So the final contrast tells us that there was a trend for productivity to be higher in natural light than in outdoor light. B equals negative 14.15, T 27 degrees of freedom, negative 12.13, and 0 as the p-value because it's so small. But if there had not been a logical set of contrasts to do, we may have just done a post hoc test, and we can get post hoc for the current data by creating a new model and running the summary for this, as well and indicating the output for the confidence intervals of the model. So I created the new model here, Tukey test, and then ran the summary for this. And then this is where you obtain the confidence intervals for the Tukey contrast. So the output shows us the results of the post hoc test, and we can see that productivity level, look here, comparison of means, in the natural light was significantly higher than compared to the low, high, and outdoor lights. Right here in the p-values, all less than 0.001, and the productivity in high light was not significantly different than in low light. P equals 0.15, and that's just what we discussed above, but this is just another way to do it. And the productivity was significantly less in outdoor light than compared to low light and high light, with the values noted below. Next, we are going to compute. Oh yeah, these are the confidence intervals that we also can run to get our reports. So to compute effect sizes, this isn't for, sorry, I'm editing this because this is for effect sizes. And had a problem with coding for this, so had to install some more packages down here. So this was DevTools. Oh, I forgot it's already installed. I guess I can talk about effect sizes while that downloads. To compute effect sizes, you have to use the values of T and the degrees of freedom from the output in the repeated measures ANOVA that we created earlier and compare the groups. So the librarying this, and then we also, after extensive Googling, figured out that this is what needs to also be installed in order to run it. So but anyway, they are setting the contrast with the effect sizes for fake versus real light in the groups that we combined. Low versus highlight, and natural versus outdoor light. So these give us the R values. The resulting values of R show that the difference between fake and real light was a medium effect, so 0.39. Between high and low light was a medium effect, 0.36. And between natural and outdoor light was a very large effect at 0.92. Thanks.